start notes at all in this class?
We did.
We did.
We did a lot of reaction.
We were down to what?
Unit to measure
We
temperature.
were down to activation energy.
No, we were at units to measure temperature.
All right. So let's. We wrote the definition for heat from something hot to something cold, and heat is measured in joules or calories, right? Joules or calories. What is temperature? Average kinetic energy. And units to measure temperature are degree Celsius, degree Fahrenheit, or Kelvin. Now, Kelvin, it's yes. All right. Celsius has been introduced for cooking. Fahrenheit was designed for weather. All right.
Wow.
But yes. All right. So Kelvin can measure all the changes in temperature that can take place. Now, so whenever a reaction is happening, all right. Let's say food is being burned and it's an exothermic reaction. Is that right? We burn wood in winter all the time. Now, have you ever seen a lava food catch fire by itself? They store it outside stores. Does it automatically burst into flames? No. You have to actually start the chemical reaction. Is that right? The wood will then eventually turn to ash. Is that right? So later on in the year, so mind that whole area. All right. Later on in the year, we're going to do a reaction between hydrogen gas and oxygen gas, and they two will explode, and it's an explosive reaction. But I can bring a hydrogen balloon to the class right now, and I can release the hydrogen gas. Do you think you will see explosions around you?
Big ones.
You won't see one at all. The balloon will just release all the gas and sit there. Nothing is going to happen. Yet the reaction between hydrogen and oxygen is supposed to be explosive, produce loud noises. The point is, there are a number of reactions that can take place, but they don't. And the question is, why? One of the reasons is because you need to provide more energy before the reaction can actually start. If we want to burn a log of wood, I need to put some gasoline on it, or I need a starter there, I need to light up a match. Once the reaction gets going, then you can get the product. Is that right? So this energy to start a reaction, write down. The energy to start or activate a reaction is called activation energy. It's called activation energy. Now, so we talked about a chemical equation last class. We said reactant becomes product. Is that right? So during a reaction, energy changes take place. The reactant has a different energy, the product has a different energy. And some of the heat is released in between, some of the heat is taken in between. Is that right? Is that how reactions proceed? Now, if we draw a graph to denote how energy changes are taking place during a reaction, such a graph is known as a potential energy diagram. All right? A graph that denotes energy changes during a reaction during a reaction. Right? So now, what did we say was an exothermic reaction? Is heat released or heat absorbed?
Released.
Heat is released. Let's make sure we know that. Heat is released. And what is an endothermic reaction? Heat is absorbed. Is that right? So now we are going to draw a graph. Whenever we draw a graph, we need an x and a y axis. Is that right? Now, here is my x axis and that's my y axis. Alright? And I'm going to say this is my reaction axis. With time, what is going to happen? My reactant is going to become product. Is that how a reaction takes place with time? And I'm going to have heat energy. I'm going to have heat energy on my y-axis, and my heat energy is going to be in kilojoules. What is the unit? Kilojoule. Okay? Now, my reactants are my chemicals. Is that right? And any chemical has what kind of energy when it's stored? It has the potential energy. Is that right? So I'm going to make up a number here. I'm going to say this is my reactant. What is that? That line is the energy of my reactant. And I would like you to give me a number in tens, please. What do you think should be the energy of the reactant? Give me a number. 20. All right. So this is 20 kilojoules. What is that number? 20 kilojoules. Is everybody able to see my number? It's 20 kilojoules. 20. Make your reactant 20 kilojoules. Did you write that down? Or you can write it beneath the reactant also. It's on the graph, right? Generally numbers are on the graph, right? Is that how you can read them? Okay. So in an exothermic reaction, is heat absorbed or released? Is it given away or is it taken in? It is given away. Is that right? Is it released? So here is an example. I have so many pens and markers. I'm giving it away. I'm giving it away. When I give things away, am I left with more energy or am I left with less energy? Less. All right? So I'm left with less energy. Does that make sense? So what do you think should be my energy of product? More than 20 or less than 20?
Less.
Less. So the line will come below. Is that right? Does that make sense? And that's going to be my product. And my product is, let's make it 10. All right? 10 kilojoules. All right? My product is 10 kilojoules. Now, is my wood going to get converted to ashes immediately? Is my reactant going to become my product immediately? No. What do I need? Do I just need time? If I sit there waiting patiently, Casey, will my wood become ash? What do we need? We need activation energy, which means I have to strike a match. I have to give my reactant some little energy before they can become a product. Is that right? So, how much energy do you want to give the reactants? 30 is too much. The reactant itself has only 20. So 5, all right? So I'm going to give it about 5 more kilojoules of energy. Is that good? That's what? What is that 5 kilojoules of energy called? That's called my activation energy. Is that right? So that is my activation energy. Everybody good? Everybody can understand what I'm writing? That's called my activation energy. So then, if I provide that activation energy, which is now, let's say, 25, oh my God, all right, which is now 25, all right, it's 25, all right, so my reactant then becomes my product. It is like a hump, is that right? It's climbing up from 20 and it's hitting its peak at 25, is that right? At 25 and then it's dropping down to 10. Pretty good? Okay. Do you understand the process so far? Okay. So, what is the energy of my reactants again? 20. What is the potential energy of my product again? 10. What is my activation energy again?
25.
Is it 25 or 5? It's 5. The activation energy starts from the reactant to the top. So it is 5. Alright? Now, so during my reaction, heat of reaction, alright? During my reaction, heat is either released or heat is absorbed. Is that right? So what is my final product? My heat of reaction is always my heat of product minus heat of reactant. Heat of reactant. What is my heat of product again? What was my number? 10. Minus, what was my heat of reactant again? What was it? 20. What is 10 minus 20? Negative 10. Did we say that in an exothermic reaction, heat will be negative? Did we talk about this before? Do you remember this? Okay, let's go up. Let's go up. Okay, this is not working. Okay, so here it is. Did we say in an exothermic reaction, heat will be negative? Did we take notes on it? Did we draw the graph correctly? You see? All right. Now we are going to draw the graph for the other reaction. Is that right? Can I erase this graph? Everybody has this? Because sometimes it's confusing for kids when I have both. Okay? So I'm going to erase this graph and I'm going to draw it for my endothermic reaction now. I have to have my axis. So this is my reaction axis and it's in time. This is my heat energy and it is in kilojoules. Okay? Now give me the energy of a reactant. So that's my reactant. Give me some energy. 5 is too less. 40. All right, 40. 40 kilojoules. That is my reactant. What happens in an endothermic reaction? I absorb. Is that right? Everybody look at me. I absorb. I take heat from the surrounding. Now do I have more or less? I have more. You see that? So give the energy of the product. Give it a number. What is that? Okay, product is 50. It's going to be 50 kilojoules. Will my reactant automatically become a product? Or do I need to give my reactant? How much activation energy do you think I should give? 10. Oh, 10 means it's right away at the product, so now it's going from 40 to 50. Doesn't work like that. Otherwise, it'll automatically convert. 5 is less, way too less. 20. Okay, so 20 means if I do 40 plus 20, what does it become? It becomes 60. That looks good. And so now my reactant has become the product. And what is my activation energy? How much is my activation energy? 20. Now, what is my heat of reaction? What is my heat of reaction? Can somebody tell me?
20.
It starts with what? Heat of reaction is always final minus initial, product minus reactant. What is that? 50 minus 40, which is equal to 10 kilojoules. Right? Is that right? Is my heat of reaction 10 kilojoules? Now, have you ever heard of a catalyst? What is a catalyst? Triggers the reaction. Is that how we define a catalyst? How do we define a catalyst? Speeds up a reaction. Catalyst is a substance that
Are we writing this?
write it on the top, write it where you have space, but you need to know what a catalyst is. It's actually biology information. I don't need to provide you with this, but I'll review it with you anyway. All right? Catalyst is a substance that speeds up a reaction. You should have known this coming into this class. Right? Good to review though. Now, the question is, the catalyst speeds up a reaction. How does it actually speed up a reaction? What does it do? So, let me tell you how a catalyst speeds up a reaction. So, do you see the reactant to the product? The catalyst actually lowers the activation energy, all right? It'll still go from the reactant to the product, but now what is my activation energy? It's going from 40 to maybe 55. Does that make sense? So, how does a catalyst speed up a reaction? Catalyst speeds up a reaction by lowering what? By lowering activation energy. All of you stop. And I would like you to pay attention to this detail, Jillian and Jennifer. All right? So, the reactant is still this energy. The product is still this energy. Does the catalyst impact the heat of a reaction? So, a catalyst does not impact the heat of a reaction. What does it impact? It impacts the activation energy. Do you get the difference? It doesn't do anything to where the reactant's potential energy or the product's potential energy is. That remains the same before and after the addition of a catalyst. Is that right? Okay. Now turn to the back page. Do you have questions there? I'm going to give you 5 minutes and I'm going to, you can discuss, you can talk. Now is the time to talk. All right? And I'm going to come back and discuss the answers. All right, go ahead. Go ahead, discuss with each other and find out the answers to those questions. Answers. So let's see. Starting with Soma at the end. Okay, now Soma, which letter in the diagram represents the total energy of the reactants, the potential energy of the reactants?
I got A, B, C, and D.
All of them?
Wait.
I need only the potential energy of the reactant, Soma. Here is my reactant.
Oh, my bad.
So what is the total energy? What is it, Soma? A, very good. Kara, what represents the total energy of the product? Products. Here is my product. And that is E, very good. All right. Jennifer, Which letter represents the total energy of the activated complex? Activated complex. C. Very good. Julian, which is the activation energy? Activation energy is B. Which letter indicates the heat of reaction? I keep forgetting his name. Daniel.
Um,
Heat of reaction is product minus reactant.
so that's D.
D.
Yeah. Or wait,
Product minus reactant.
C.
See? My reactant is higher.
F.
What is it?
F.
F. That is correct. Alright? Heat of reaction is F. Joselito, is it an endothermic or an exothermic reaction? It is an endothermic reaction. Now, Freda, which letter indicates the activation energy for the reverse reaction? Meaning, you now consider this to be a reactant and you consider this to be a product in the reverse reaction. So this is my energy of reactant, this is my energy of product. What is the energy of activation? D is correct. Which letter indicates the heat for the reverse reaction? Yes, Sarah? Product minus reactant. F. It is correct, but it's minus F. Alright? It's minus F. Is because, Bitil, what is the reverse reaction? Is it exo or endo? The reverse reaction is exo, therefore F will be negative. Does that make sense? In an exothermic reaction, it's always, heat is always negative. Ravan, if a catalyst were added, would the heat of reaction increase, decrease, or remain the same? Heat of reaction. Very good. It's going to remain the same. Use the axis below to draw the potential energy diagram for the following conditions. All right. I'm just going to draw it for you. All right. So here is my potential energy diagram. And what is the potential energy of the reactants? What is it? 100. Is that right? So I'm going to make up a line here and call that what? 100 kilojoules, and that is my reactant energy. Everybody good? Now, what is the energy of my product? 50. Is it more or less than 100? Less than. So, I'm going to call this my product, right? That's my product. And what is the energy of my product? 50 kilojoules, correct? Now, when my reactant become product? No. What do I need to provide it with, Cat? Did I come to you? No. Okay. So what is the activation energy given here? What is the activation energy given here? 25. Is it 25 more than the reactant? Or is it from the base 25? What is it? It's from the reactant. So it's actually 125. And I see my jump going this way. Is that right? Do you agree? Yes or no? Okay. So given that, Parker, I have drawn my graph now. Is this graph exo or endo? It is an exothermic reaction. Coming to Kate, what is the heat of reaction? KD, right? Yeah. Okay. That's the activation energy. How do I calculate the heat of reaction? Reaction is calculated by, what is heat of product? 50. What is heat of reactants? 100. So it's 50 minus 100. What is that? It's negative 50, and it explains because it is an exothermic reaction. Does that make sense? So the sign is very important. Now, I'm going to draw the effect of a catalyst. How do you draw the effect of a catalyst? You draw a dotted line starting from the reaction to the product, but it should have what? What is lower? The activation energy is lower. Do you understand? Now, I think on your homework sheet in the back, you will have to practice potential energy diagrams. Is that right? Yes, Soma.
How do you know if it's exo?
If heat is
within the graph.
If heat is released, Soma, we said, as I'm giving away, I have less. Right? The reactant gave away. That's why the product is less. When it's giving away, it is exo. If it is gaining, it is endo. Right? Does that make sense?
So if it was endo, the graph would be, how would the graph go?
So if it has gained energy, where do you think your product line would be? This is my reactant. Higher. That's my endo.
Got it. Thank you.
All right? Good question. All right? Very good question. I see that she's thinking. I see that Jelani has his head down. I don't know if he's participating. Jelani, are you feeling okay? He's fast asleep.
He's gone.
Okay. Guys, just as I get to know you students, you have to know me as a person. All right? I am very big on the body language in class. I read a student's body language. I find out if a student is interested in learning, if the student care about themselves, if the student want to get out of my class, want to be successful in life, what is their motivational factor? If I just had a student the other class, all right? The student was sitting like this, right up in front. All right? Do you think the student is interested in listening to me or what I'm teaching? The student is already predetermined not to learn. Can I ever reach across to him? If I see your head up like this going on to sleep, if I see your eyes shutting tightly in my class, all right? I'm watching you. Okay? I do not like such behavior in class. I need your back straight. I need you to be attentive in class. If you don't want to learn, I cannot teach you. Do you understand? If you don't want to learn, I cannot teach you. Does that make sense? First of all, you should be willing to learn. Right? You should care about yourself more than I care about you. Do you agree? And how do you show it to me that you care? I will watch you. All right? Now, let's go on to the notes page. Did you pick this up by the door? All right? Write down, energy is the ability to do work. Energy is the ability to do work or produce heat, right? What is law of conservation of energy? Energy cannot be created or destroyed. Energy cannot be created or destroyed. Guys, this notes page you have to memorize. Does that make sense? Whatever you're writing down, you should know. Now, chemical potential energy is the energy stored in a substance because of its composition. What is the symbol for heat? Q. What is heat? Energy that flows from hot object to cold object. In an exothermic, heat is released. In an endothermic, heat is absorbed. Heat is measured in calories. What is the definition for a calorie? The amount of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius. All right? Joule is the SI system, all right, metric system. Conversion factor is 1 calorie is 4.184 joules. What is specific heat? Specific heat is the amount of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. The symbol for specific heat is C lowercase p. P is a subscript, not lowercase, subscript p. Units are joules. It's the amount of heat required to raise for 1 gram by 1 degree Celsius. Is that right? So joules per gram degrees Celsius. All right? This is a very important equation that you have to memorize. You're not able to follow my handwriting?
No, it's not.
So fast.
Am I?
Yeah.
Are you with me so far? Should I wait?
What is that little symbol next to the calorie?
What's that dog?
This one?
Like
Cow.
next to it?
This is calorie equals 4.184.
Wait, what's
Julie?
this?
This one? This is C. It's at constant pressure, so it's the symbol P. Okay? What does Q stand for? Q stands for heat. Alright? And heat is measured in what units? Calories or joules. What does M stand for? Mass. Mass is measured in what units? Grams. Those are the units. Are we good? All right, let's go to the next page. Okay. What does CP stand for? Specific heat. And it's joules over grams degrees Celsius. That is the unit for specific heat. What does delta T stand for? Change in temperature. Change in temperature. And delta T is always equal to T final minus T initial. So what is the final temperature minus the initial temperature? Okay? Now before I go on, let me talk about, oh, do I have to go back? Have you not written it yet? All right. So here is, write it out. Are we done? Okay. So the next concept that I'm teaching you is this. I made you write notes, but I never talked about it. Is that right? What I'm teaching you is this formula. Q equals M times Cp times delta T. Okay? What does this mean? Whenever I heat something up, does it absorb heat energy? I can put a pot of water on a stove. It will absorb heat energy. It will become hot. Is that right? How hot will it become? What is the numerical value for how much heat energy that substance is going to absorb? Does that make sense? Those are the calculations we are doing in this class. Now, if you leave a hot coffee cup outside, what will happen? Eventually it will get cold. It's losing its heat energy. Is that right? How much heat energy is it losing? What are the factors on which this depends? Now, if I were to heat, let's talk about mass. What is this? This is mass. What units do we measure mass in? Grams. If I had a container, a beaker with 20 grams of water, and I had another container with 100 grams of water, which do you think will require more heat energy to heat up? So, more the mass, more the heat energy it requires. Are you able to make the connection? Alright? What did I say this was? This is change in temperature. Alright? That is what? That is change in temperature. Say my mass is fixed. Okay? Say I have two objects. Both mass are what? 20 grams, 20 grams. There is no change in mass. But then I want to change this temperature from 10 to 40 degrees Celsius. From 10 degrees Celsius, I want it to go up to 40. And then for this one, I want to go from 10 to 100 degrees Celsius. Which do you think will require more heat energy? Which one will require more heat energy? So 10 to 100. So more the change in temperature is 90. Do you agree? 100 minus 10 is 90. And in this case, the change in temperature is 30. More the change in temperature, more is the amount of heat energy required. Do you agree?
Yes.
Now, the third situation is, what is this? What does this stand for? Specific heat. And what is the unit of specific heat? Joules per gram degree Celsius. Is that right? So this situation is, I have two blocks. Alright? Both their masses are 20 grams, 20 grams. Alright? I want to change the temperature from 10 to 40. I want to change the temperature from 10 to 40. No change in all that. But one is made of wood, one is made of metal. Which do you think will become hot faster?
Metal.
On a hot day, Soma, if you go to a park, the sun is shining. You see two benches on which you can go sit down. One is made of metal, one is made of wood. Which would you prefer to go sit on?
Metal.
Why?
It's
The metal takes up a lot more heat energy. It heats up much more quickly. Is that right? Rather than the wood. Is that right? So, you can fix the mass, you can fix the change in temperature, but it still depends on the type of substance. Is that right? It's specific to the substance. Metals absorb heat a lot faster than other materials like wood. Is that right? Conductors, heat conductors will absorb heat faster. Does that make sense? Yeah. Okay. So that is that equation. Do you understand? And There is an activity that you can do. I'm going to post, you know how we learn how to take measurements, have one estimated digit and all that. Julani, sit up straight. I mean it. Sit up straight, back straight. Alright? I will post a similar activity with an answer key on Blackboard. You can just do it to understand this equation. Does that make sense? Alright? But I'm not going to make you do it in class. So this is the equation we are going to learn. How much heat energy does a substance take in or lose? Does that make sense? Okay. So now let's go back to the problems. Do you see this? Okay, we are going to do the problem. I write. I write. You write. Okay? Now, I see this. Parker was the last person who answered. Kat, did you answer the question for me? Katie also did? Alright, Austin. I see 1.32 grams. What is it? Is it mass? Is it heat? Is it specific heat? Is it change in temperature? What is it? That is mass. So when I look at a number, I like to write down what it is on top of that. I just triangle it because the red thing is blocking the view. Is that right? If I write, you write, David. On your paper, you should be writing. Jelani, I see two temperatures here. Right? You see that with me? What should I do with the two temperatures? What should I do with the two temperatures, Jelani? Huh? Find the difference between them, subtract them. Can I say this is T initial and that is T final? Right? And my delta T is always equal to my T final minus my T initial. Do you guys agree? Okay. Now, Andrew, what is 0.4494 joules per grams per degree Celsius? What is that? That is my CP. Everybody good? Did we locate the variables in the given problem? So what are they asking us to solve for? Calculate the energy. What are we solving for? Q equals what? You're solving for Q. So what is the equation? Q, wait a minute, Kat. Q equals, Alex? I need to know the equation. Q equals M times Cp times delta T. Is that right? What do I substitute for M? 1.32 grams times, what is my specific heat? 0.4494 joules over grams degree Celsius times, what is my delta T? 46.0. My delta T is 46.0 minus 25.0, 21.0. So that's times 21.0 degrees Celsius. Do you have a calculator with you? If you have it in your backpack, you should be taking it out.
12.4.
Okay. Watch me as I do the problem. Dimensional analysis is coming back. Grams and grams. Is it in the numerator and the denominator? Will they cancel? Yes or no? Degree Celsius in the numerator, degree Celsius in the denominator. Will they cancel? What will my final answer be in? Joules. What do I do with the numbers? Multiply. Is that right? So when I multiply, what does my calculator give me as the answer? 12 point, okay. So what is the answer? 12.457368. Should I report such a long answer? How many sig figs must I report the answer to? 3 sig figs. Alright? I should report it to 3 sig figs. So what does my answer become? 12.5 joules. Everybody good? Did you understand the problem? Julian? No? Daniel, is it difficult?
No, it's just
Do you understand? Okay. Now, I need you to make small corrections here. Please do not say this is kilojoules, just call it joules. Alright? Get rid of the K there. Oh, my smartboard is not that well aligned. Get rid of the K there, alright? And make it just joules. Get rid of the kilograms and make it just grams. Okay? What is my first step? Write out the equation, but before that, I need to identify my variables. What is 52.5J? Is it Q? Is it M? Is it CP? Is it delta T? That is my Q. So the Q is given. What is 1.02 G? What is that? That's my mass. So my M is given. What is 11.2 degrees Celsius? What is 11.2 degrees Celsius? Kate, are you on your phone?
No.
Okay. Delta T. It's both. The difference is given already. Alright? That is delta T. What am I solving for? What am I solving for? Specific heat equals what? Is that my equation? Josh, are you following along? Okay. So now I'm going to substitute in my equation Q equals M times CP times delta T. Is that right? What value will I substitute for Q? 52.5 joules. Is that right? What is my M? 1.02 grams. I don't know my CP. Am I solving for CP? Can I call my CP just X? Right now I'm going to call my CP my variable X, like math. Alright? Times, what is my delta T value? 11.2 degrees Celsius. Okay? Now what do I do with these two numbers? Multiply them. So what do I get when I multiply those two numbers? 1.02 times 11.2. I get 11.424. Let's not forget units. What are the units? There is G, and then what else is there? Degree Celsius is there, and what else is there? X. X is my variable that I'm solving for. Is that right? Equals, on this side, it is 5.25J. Now I need to solve for X. What do I do with all the numbers and units that are before it? Divide it by all of that. Is that right? So I'm going to divide this by 11.424 grams degrees Celsius. I'm going to divide this side also by 11 grams degrees Celsius. Got that? All this will cancel. Is that right? So what do I do with those two numbers? Divide now. Is that right? So I got 52.5 divided by 11.424. And what do we get? My answer, X equals 4.5955 and so on. How many sig figs must I round my answer to? 3 sig figs. Is that right? So 1, 2, 3. So I'm going to round to 1, 2, 3. So what will this number become? 4.60. Let's not forget the units. What are the units? Joules over grams degrees Celsius. Did you understand? Is it good? Did we follow the problem? All right. Let's do the last problem also.
Ugh.
So let me get rid of these things.
Yay, scientific notation.
Alright, what is this?
Scientific
The unit is J. David, what do you think is J? Is it Q? Is it M? Is it CP? Is it delta T? What are the units for CP? Go look at your notes. What are the units for CP? J over. So is that CP? It's just J. What is it then? It is Q. Hey, in real estate, it's location. Is that right? If it's location, good location, it's very expensive. In heat problems, what is it? Units. It's units, units, units. Okay? You have to pay attention to units. What is this, David? That is mass. What is this? Joules over grams degree Celsius. So let's write the equation. What do you think you're solving for in this equation? Are we solving for delta T? Q equals, what is the equation, David? Q equals
mass times CP times
alright. So what will you substitute for Q? This thing moves 3 places over, so let's just keep it 54254J. Is that right? What is my M? 742.1G. What is my specific heat? 94 what units? What am I solving for? Delta T, can I call my delta T my X? Can I call my delta T my X? What do I do with these two numbers now? Multiply them. So 742.1 times 0.4494. I get 333.49974x, right? But before that I have to write my units. My grams and grams will cancel. Is that right? So what is the only unit I am left with? Joules, degrees, Celsius, and X. Is that right? So if I need to solve for X, what do I do? Divide by the same number. Is that right? So I'm going to divide, alright? I'm going to divide on this side by 333.49974 joules over degree Celsius. Please watch here for a minute. Please watch this side. Now I have 333.49974, right? What's the unit? There is joules. What will happen if there is joules in the numerator and joules in the denominator? It cancels out. This Celsius is in the denominator. Is that right? Where will it go? It will go to the numerator. Do you remember those fraction rules? Do you remember, like if I have a number 1 by 2 divided by 3 by 4, how do I write it? 1 by 2 times 3 by 4. Remember that? Remember doing such math? So what will happen to this? If it were in the denominator, what will happen? It will actually go to the numerator. Does that make sense? So what is the only unit I am left with? Degree Celsius, correct? Yes or no?
Yeah.
So now what is my math? 4524
13.57 degrees Celsius. That's rounded.
So I see my calculator answer. I get my x to be equal to 13.56522. But how many sig figs must I report to? 4. 1, 2, 3, 4. So what will that become? 13.57 degrees Celsius is my change in temperature. Did you understand this problem? So in the given expression, you will be asked to solve for any of the variables. Do you understand? So your homework will be to learn potential energy diagrams and do practice problems on this. Now, can you all go to your warm-up, please? Please go to your warm-up.
Look at the back.
Yeah, go to the back of your warm-up. Please complete it and turn your sheet in with your name on it. Right, Mr. Friend? Please do the back and turn in your sheet. You know what? I finished early, Miss McCrane.
Yeah, this is a quick class.
They can start working on their homework now.